can be any fluid. It may be liquid or it may be gases. And we know that the cylinder must be strong enough to bear all kind of stresses, pressure, which these fluids exert on its wall, or cylinder should have such kind of thickness or strength that it does not break when these fluids are being, or when it is filled with these type of fluids, which can be any types of liquid and gases. Some of the common example of cylinders which we have seen in our daily lives as well are the tankers or petrol tankers or water. And here I want to emphasize on one thing, that we have seen small pipes carrying water. So these pipes are also an example of a cylinder, because in these pipes the liquid is moving, or liquid is being stored in a closed duct, and liquid is exerting the pressure on the walls of these pipes. So physically, these type of pipes also have same kind of stresses which are being induced in a cylinder. Now in this figure you can see different type of the cylinder. These are the petroleum tanks or storage tanks. In these, during the design of these tanks or these cylinders, we have to consider different type of stresses, and based on those stresses, we determine that what type of material we are going to use, how we are going to arrange that material, and how what type of joints we have to install in this type of cylinder, and how we, and what type of, even the type of boards that we are using is also decided based on the stresses that we calculate, considering the amount of liquid or type of liquid that we have to store in a particular tank. So broadly we speak, the cylinders are divided into two types, which are thin cylinders and thick cylinders. So what is a thin cylinder? The cylinder in which the diameter or the diameter of the cylinder is 20 times or more than 20 times of the thickness of the wall. So in this case, you can see that the diameter is significantly greater than the uh, thickness of the wall. So this type of cylinder is called as a thin cylinder, and in this thin cylinder, when some kind of a fluid or some kind of liquid or gases are present in it, three type of stresses usually occur, which are circumferential or hoop stresses, longitudinal stresses, and radial stresses. Here I want to uh, state one assumption. It's not an assumption, it's a proven phenomenon, that obviously there are three type of stresses in these type of thin cylinder, that are circumferential, longitudinal, or radial. But when we will be solving the numerical examples of the problem, we will see that these radial stresses will have very small magnitude compared to these circumferential or longitudinal stresses. So in most of the cases, these radial stresses are neglected because they won't have much larger impact. For example, when we'll be solving the example, I will show you mathematically as well that these circumferential stresses will have the values something like 15,000 psi. This longitudinal stress will have a value something like 10,000 psi, but this radial stress will have a value of 200 psi. So now these 200 psi won't have much effect on the stresses or overall condition of the material. So that's why in most of the cases these radial stresses are neglected when we're solving the stresses, or when we are reporting the final state of stress of any cylindrical element. But this is true only in the case of thin cylinder. In the case of thick cylinder, these radial stresses also become important, and that will be we will discuss that in when we'll be studying the thick cylinder. So now our focus is to study the thin cylinders. So let's suppose that this is a cylindrical body, and it satisfies the condition that the diameter is greater greater than 20 times of the thickness. So this cylinder is basically a thin cylinder. Now in this cylinder, let's suppose that both these walls are fixed, or there is a covering on this wall. For example, you can see that these two ends of the cylinder are closed with walls perpendicular to the shell. So that basically means that there is a fluid inside this cylinder, and both its walls are fixed. So when the flow is inside the cylinder, it will exert different kind of stresses. One is we know that it is the radial stresses, and another one is circumferential or hoop stress. Now let's see what is radial stress. Now, radial stress at any point of the wall thickness is always equal and opposite to the internal pressure. Now, when there is a fluid in a cylinder and you are looking at it from this direction, this fluid will be exerting a pressure on the wall or on the wall of this cylinder. Now, exactly equal and opposite force or resistive force will be exerted by this wall of the cylinder, and this resistive force is called as the radial stress. For example, if this is Pi, if this overall is Pi, let's say, and over here there is one component, and to resist this, there will be one component that is exactly equal and opposite to this one. Similarly, over here there will be one component. Over here there will be one component. So these stresses which are exactly equal and opposite in direction are known as radial stresses. So if I represent it mathematically, it will be radial stress that will be equal to uh, internal pressure or the pressure exerted by the fluid, and with a negative sign because these radial stresses are acting in the negative direction. So this is the concept of radial stress in a thin cylindrical case. Now let's talk about the longitudinal stress. I have shown you previously that let's suppose this is our cylindrical element, and if we are moving in the longitudinal direction, so what is the longitudinal direction or longitudinal axis? It is the axis that is parallel to the length of the cylinder. Now if we why these this is an important concept, that why these stresses are called longitudinal stresses. So if we are moving along the length of the cylinder, there are different cross section along the length. If I am moving along the length and I, let's suppose, cut a section over here, or I can cut a section over here. So these are different sections that I can make in a cylindrical element when I am moving along the length. So let's suppose this is my section under consideration. So this section I have shown over here, and in this section, now this is my whole cylindrical element. Now there isn't any cover over here, but this cylindrical element will have a cap on the left side. So the fluid is moving inside the cylinder. Now this fluid that is shown by the blue lines will be exerting a force on the wall of the cylinder, or on the on the wall at the left end of the cylinder. Now this fluid will be exerting the force over that wall, and to resist that force, there will be stresses that will be acting, or the resistive stresses that will be produced on the wall thickness of the cylinder along the whole circumference of this cylindrical element to resist these type of the forces. So the force exerted by the fluid is shown by these blue arrows, and the force exerted, or the resistive force, I should write it over here, or the resistive force or resistance to this force will be provided by these forces, and this resistive force is known as longitudinal stress. So I would repeat it again, that why it is called longitudinal stress, because there are numerous such sections along the length of the cylindrical element. So that is why it is known as longitudinal stress. And how would you define it? That the resistive force acting at cutting wall section which is equal to the force produced by the bursting pressure at the cylindrical wall. So this is the bursting pressure, or the force exerted by the liquid on the cylindrical wall, and this is the resistive force, and this resistive force is known as longitudinal stress. So how will you calculate it mathematically, or how will you prove it mathematically, that the bursting force is equal to the resistive force? So this is the bursting force shown by the blue arrows over here. So this pressure is P, or the force is P. If I want to, the stress, or this P is internal stress, okay, and this sigma L is longitudinal stress. So now I know that the bursting force is equal to the resistive force, because both of these forces are acting in the opposite direction. So if I want to calculate the force out of the stress, so force is equal to, or I can say sigma is equal to F over A. So the force is equal to stress into area. Okay. So for this P force, how much is the area? Obviously, this force is acting on the entire wall of the cylindrical element. So I have to consider that whole area as the area affected by this fluid, or the area on which this fluid is exerting the force. So this is the stress. I will multiply it with the area of this wall, that is pi d square, simple because it is a circular element, so that area will be pi d square over 4. And the what is the resistive force? The resistive force is this longitudinal force, but you can see that this longitudinal force is only acting along the circumference. It is not on the whole is open. Okay, so it is not acting on it is acting on the surface only. So
Sir, sir, we are unable to
सर
understand.
आपकी
The
आवाज
connection is continuously
नहीं आ
breaking.
रही.
सर आपकी बात सही से नहीं आ रही, कट कट के आ रही है. So can you hear us?
can you hear me now?
Yes, sir, we can hear you.
Is it better or still not good?
Better now.
Hold on, I will join the meeting again. Can you hear me now?
Yes, sir.
Okay. Okay. So from now, from this figure, I was telling you that this longitudinal stresses, or these longitudinal stresses, are acting only on the circumferential area. So we have to, when we are calculating the force due to this longitudinal stresses, we have to multiply this with the circumferential area only. So this is longitudinal stress, and this over here is my circumferential. You know that the circumference of the circle is pi d, and if you multiply it with the thickness, you will get the area of this. Okay, so we know that the bursting force is equal to the resistive force. This is the bursting force which is exerted by the fluid pressure, and this shown by the red arrows is the resistive force. So if you simplify this equation, you will get this simple formulation for longitudinal pressure or longitudinal stresses. So in this formulation, you can see that if you know the internal pressure, if you know the diameter and the thickness of the cylinder, you can calculate that how much is the longitudinal stress in this case, in the case of this thin cylindrical element. So the third stress that we were discussing is the
Excuse me, sir.
yes.
सर जो D है ये इंटरनल डायमीटर या एक्सटर्नल?
D. Okay, yeah, this is an important concept. D is actually the thick. For example, if you see in this figure, this is the point load. If I consider only one component of this overall longitudinal stress. Now let's look at this one component. Now this component is a point load. Either this component can act along the whole thickness. For example, if I say that it is acting on the whole thickness, it will be something like this. But in this case, it would become UDL. So to counter such issues, for example, if I show it over here, and if I say that this single unit load is acting on the whole component, it will become something like this, that over this whole body or over this whole thickness, there will be one force that will be acting. So just in order to avoid this confusion, there is one assumption in the computation of this d distance. They would say that this d distance is from the center of one thickness to the center of other thickness. For example, if you are provided with the overall diameter or the external diameter of the cylinder, let's say it's 10, and if you provided with the thickness, let's say the thickness is 2, so the d I will call it as d dash. So the actual d that we need to consider over here is from the center of this thickness to the center of this other thickness. So if the external diameter is 10, I will subtract 2 from here, and this will be my diameter d. So just to avoid this confusion, to make it to avoid the scenario of making this point load as a UDL, we have assumed that this UDL is acting at a center point of the thickness. Have you got the answer?
यस सर सर कर सर नज़र नहीं आ रहा, पता नहीं चलता आप कहाँ पे एक्सप्लेन कर रहे होते.
Okay, I will try to make it work. Okay, and the next thing is these hoop stresses or transversal stresses. These stresses are also called as circumferential stress. Now you have to remember now you have to differentiate or keep this thing always in mind that these stresses are called as circumferential stresses as well. Now the previous one, although they were acting on the circumference, but they were not called as the circumferential stress, but they were called as the longitudinal stress, because we were moving along the length of the cylinder and cutting different sections. But in this case, if this is the cylindrical element, okay, let's suppose that I will show from previous figure. Now let's suppose that this is the cylindrical element and we cut the section in this direction. So that basically means that this is the circumference of our cylindrical element. So in this circumference, we have numerous such sections that are running parallel to the length of the cylindrical element. So for this reason, these stresses are called as circumferential stress, because in this one you cut the section that along the cut the section perpendicular to the circumference of the cylinder that runs along the length of the cylinder. So in this case, basically in the case of longitudinal stresses, you are cutting the cross section perpendicular to the length, and in this case, we are cutting the section perpendicular to the circumference. We are cutting the section perpendicular to the circumference, and this is the reason that these stresses are called as circumferential stress. Now let's assume that this is the cross section. In this cross section, this perpendicular force that is acting is known as hoof stresses. Okay, this force that is acting along the, we have already discussed that this is the longitudinal stress, and perpendicular force to this cross section stress. Now, if there is fluid over here, that will be exerting forces along this whole length. Call that force as Fy. This force is being resisted by this thickness or by this
सर नहीं समझ आ रही
component of the
आवाज
stress
बहुत ज्यादा
sigma
ब्रेक
L,
हो
which
रही है.
is acting
सर आपकी
this
आवाज नहीं आ रही
this flux is equal to the again
Plus
is it
शायद
getting better
इंटरनेट
now?
ऐसा नहीं सर अब ठीक है
Still there is an issue.
सर अब ठीक हो गई है
सर आपकी आवाज
आवाज
नहीं
नहीं
आ
आ
रही.
रही सर आपकी
11 बजे वो कंक्रीट की क्लास भी है सर.
सर JS4G इस्तेमाल करें शायद उससे ठीक हो जाए
Is it clear now?
Yes sir, it's clear now.
Okay. Okay, so when there is a fluid over here in this cylindrical element, and that will be exerting the force over the whole cross section. To resist this force that is acting in the y direction, there are these hoop stresses which are acting in the thickness of the cylindrical element, because obviously the material has to provide the resistance to the applied force. So the force is acting on the force of the fluid is acting in the downward direction, and these hoop stresses are acting in the upward direction. So again, the concept is same, that the applied force is equal to the resistive force. So the applied force, which is basically the force induced by the internal pressure, is equal to, can I say that the applied force is equal to again the pressure, which is basically the stress, or I can call it as Pi, into projected area. Now this pressure is acting over this whole area, that is d multiplied by length. For example, over here there is a force, and this force is acting along the entire length of this cross section. So the applied force will be equal to P into dl, because it is acting over this whole area. And what is the resistive force? The resistive force is basically the force due to this or the force that I have due to the stresses that I have shown on the thickness sigma h. Now if you carefully look at this figure, this sigma h is acting on this area. If this is the thickness and this is the length, the sigma h will be equal to sigma h into LT. But again, in this cross section, when I cut the section perpendicular to the circumference, I have two thicknesses in consideration, one on the right side and one on the left side. So the resistive force will be represented as, for example, force is again stress into area. So force is equal to stress into area. So the stress is sigma h multiplied by what is the area of this wall, that is length into thickness. But again, there are two areas or two wall thickness in one cross section, so we have to multiply it with the two. So again, we will apply the same concept, that the applied force is equal to the resistive force. The applied force is PdL. P is the internal pressure or the internal stresses. Length is again the length of the cylindrical element. D is again the distance from the center of this thickness to the center of this thickness, which is shown over here as well. And what is the resistive force? This same force. And when we simplify this equation, we are going to get this answer. So this is the formulation to compute the hoop stresses in in the case of thin cylinder. Now, if you look at this figure, there is not this calculation or derivation. There is not much difference. So the only difference is that the longitudinal stress is half of hoop stress. So if you can calculate one factor out of these, you can use this formulation to calculate the other factor as well. And you will see in some of the complex numerical cases, this formulation will be changed a bit. So in that case, we won't be using this formula at all. We will simply calculate these hoop stresses, and based on this assumption or based on this conclusion that the longitudinal stress is half of the hoop stress, we can calculate the other factor easily.
सर
Excuse me, sir.
Yes.
सर कंक्रीट में सर तनोली ने ज्वाइन कर लिया तो दूसरी क्लास कंक्रीट की शुरू हो गई है.
Okay. I think you can join that meeting and we can have another 30-minute session. Do you have a class at 1 p.m.?
Namaz at 1 p.m.
No, sir.
What do you mean by no? You mean is there a class? Or we can have a meeting
Sir, there is
around.
no class.
We can meet around 1:20. Is that feasible for all of you? 1:30. You have enough time for namaz then.
ओके सर.
Sir, why not at
At
2 p.m.?
2 p.m. Is 2 p.m. fine for all?
Yes, sir.
Is okay. So we
Yes,
will
sir.
have another 30-minute session at 2 p.m. just to conclude this lecture. So you can join the other meeting now. Okay.